Hello everyone, welcome back to my channel. Today I will be working on another problem, number 199, binary right tree right side view. It is a medium complexity problem. Now, most of the problems that I work on my channel are more like challenges that mimic the actual interview process. And although this is also the case for this one, but most of the time I have not worked on problems in the past, but this one I have worked on in the problem. I have worked on the problem in the past, so today I'm going to try to take another knack at it with a new algorithm. I submitted the problem back in 2019, which was 2 years ago, but I have learned a lot since then, and hopefully we can optimize the algorithm and make sure we don't get the wrong result. So let's go through the problem. The first step is to read and understand the problem. Given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. So in the list, we would need to return 1, 3, 4 because we have to be imagining ourselves as somebody who's standing on the right side. And the person standing on the right side of this current tree would only see 1, 3, 4, and then the values 2 and 5 are on the left side. This is a pretty good visual representation, but one thing that is might be an edge case to some people is, let's say you have tree values that look like this, but instead of 4, let's say we don't have anything, right? So then we have 1, 3, and then null here. In that case, do we just return 1 and 3, or do we return 1, 3, and 5? Because you have a person that's standing on the right side, so if there's nothing here, then you would be able to see here. So we have this good feature on Tree Visualizer, and I'm not sure if it comes without the subscription, but I guess you guys can. I have the premium subscription, so I don't know if this is only for people who has the premium subscription. Excuse me. So let's try to run this and then see what we get, because this could be an edge case. So it is 1, 3, 5. So other than that, we are given the constraints. The number of nodes in the tree range from 0 to 100. So that is the number of nodes, and it is a binary tree, so it is not a binary search tree, but for this problem it does not matter anyway. So the possible values range from -100 to +100. And that's pretty much it. I don't think there are any other edge cases to consider, and we've understood the problem. So now let's discuss the algorithm. So the way we can do this is by using a DFS traversal. So in normal DFS, we have in order, pre-order, and then post-order. In pre-order, we have root, left, and right. But in here, what we can do is we can do root, right, and then left. So it would be pre-order traversal, but reversed. So instead of root, left, and right, we would do root, right, and then left. So we would traverse all the right subtrees and then get something. So if once we go down a level, let's say we go over this edge case where this side is null, then for that particular level, we can just return null. And then when we backtrack back to that level, if we see that the output was null, then we can, so after that, so it would be right and then left, and then it would go to right again. We can just add a single value here. But if and the way we are going to do that is by using a hash map. So hash maps will traverse root. We will add for that level is 1. Then we will add the next right. If it is null, then we will add like -1 because hash maps do not allow for null values. So because there's a value here, we will just add 3 at level 1, and then we will come here, and then instead of just backtracking back to 3, we will first check if it is null, and if the map does not contain any value, then we will add -1. Then we will backtrack back to 2, and then if it contains a value, that is non-negative 1, then we don't add it. But if it does contain a value that is negative 1, then we add the recent right value for that level. So this problem can be solved using hash map and DFS pre-order traversal, but in reverse. So we can actually go over the time and space complexity in a bit after we complete the coding portion. So let's start coding. So for this, let's create a list of integer list equals new array list. And then we can just create a function called preorder, or a method called preorder, and then we pass in the root. And we also need to pass in the map. So the map needs to be in order of the levels, right? So what we can do is create a tree map to ensure that the level of the tree is maintained, and for that we're going to use integer map equals new tree map. And then for that we pass in map. Tree node root, and you can just pass in map right here. If root equals null, we just return, like we backtrack, but we're going to need to add something to the map. I forgot the level, so here we'll just pass in 0, and then int level. So what we need to do is if map.contains key level, then what we do is if map.get level does not equals negative 1, then what we do is map.put level, or we could actually use replace, but because it's a hash map, it'll do the same thing. It might just be that replace works faster in the interface of map. Map.replace level, and then whatever the root.val is. If otherwise, what we do is map.put level, and then the root.val. So we will always know that we have the right value. So in here we just call preorder again. But this part is very important because order of operations and recursive calls is very important. So we do root.write, and then we pass in the map, and then we pass in level +1 to increment. And then we do the same thing, root.left this time, map, and then level +1. And then in here, so let's say we are at this level right here. If map.contains key level, we will add, if it contains key level, and we check if map.get level equals -1. So if map.contains key level, it does not, then we put in level. We come here. If map.contains key level, it does not. We put in 1. If map.contains key here, level, so we come here, right? If root equals null, if the root is null, then we add, so once we come here, if the root is null, then we add -1 to it. But I just want to make sure that's covered. In here, if the map.contains key level, if the map.get level equals -1, then we replace it. Otherwise, we will just continue. And then in here, we can just do our edge case of if it is null, then what we need to do is map, hold on. So we come here to the right, and let's say it's null, right? In this case, if it's null, then we will do map.put -1 root. So sorry, we will put map.put level and then -1. So let's say this is null, then we would put -1. Then we would return, and then we come here, and then we check if root equals null. It is null. Then we would put -1. That's fine. So let's say we come here. We don't always want to put in, because let's say we had something here, but then we backtrack and then we find if map dot contains key level, okay, so if it does not contain key level, then we put, because let's say we come back here, this was the edge cases that I was thinking about. So let's say we come here and there is a value for 4, right? And this is null. So if it does not contain any value for this level, and we know that it is null, then we put level and then -1. Then we backtrack, then we come here. If map.contains key level, it does. Then we get if map.get level equals -1, it does not. Then we go to the right. Then we go to the left. If map, then we check if root equals map.contains key level, it does, because we already put in -1. Then we backtrack, then we go to the right, and then we check if map.contains key level. It does. If map.get level equals -1, it does. Then we do map.replace level and then root.val. If it doesn't, then we just put in level and then whatever that value is. And then in the end, we just traverse the map, and what we need to do is for int I map.key set, and then what we do is if map.get I does not equal -1, and what we just do is we do list.add map.get and in the end we just return the list. List.add map.get yeah, because that will give us the actual value, and then we traverse. Okay, that should work. Let's try to run it and see. Pre-order is return type required. Oh, void 135. Let's run all the edge cases. 1, 5. Okay, let's try to submit this. Okay, cool. So the runtime was 4 milliseconds faster than 9.62% of Java. So the time complexity for this algorithm is actually, because we are using DFS, and we are concerned about the call stack. So every single stack frame that is called, that is made inside the DFS function will be of n, because, sorry, that is for the space time. I apologize. So the space complexity will be of n, and time complexity will also be of n because we are traversing every single node. Let me know if you guys think that there is a way I could have improved. Thanks for watching. Bye.